Let's put train test into action. So you might remember that a regression can be thought of a form of supervised machine learning. So let's just take a polynomial regression, which we already covered earlier in this course, and use train test to try to find the right degree polynomial to fit a given set of data. So just like in our previous example, we're going to set up a little fake data set of randomly generated page speeds and purchase amounts, and I'm going to create a weird little relationship between them that's kind of exponential in nature. So let's go ahead and generate that data. It's going to use a normal distribution of random data for both page speeds and purchase amount using this relationship here. So next, I'm going to split that data. I'm going to take 80% of my data, and I'm going to reserve that for my training data. So only 80% of these points are going to be used for training the model, and then I'm going to reserve the other 20% for testing that model against unseen data. Okay? So I'm just going to use Python's syntax here for splitting a list into the first 80 points are going to go to the training set, and the last 20, everything after 80, is going to go to test. So remember that from our Python Basics course. We covered that syntax before. And I'll do the same thing for purchase amounts. Now in the slides, I did say you shouldn't just slice your data set in two like this. You should randomly sample it for training and testing. In this case, it works out because my original data was randomly generated anyway. So there's really no rhyme or reason to where things fell. But in real world data, you'll want to shuffle that data before you split it. And there's a random.shuffle method you can use for that purpose. Also, if you're using the pandas package, there are some handy functions in there for making training and test data sets automatically for you. But we're just going to do it using a Python list here, just to keep it simple. So let's visualize our training data set that we ended up with. So we'll do a scatter plot of our training page speeds and purchase amounts, and it looks like that. Basically 80 points selected at random from the original complete data set. Has basically the same shape, so that's a good thing. It's representative of our data. That's important. And our remaining 20 for testing also, has the same general shape as our original data, so I think that's a representative test set too. A little bit smaller than you would like to see in the real world for sure. You'd probably get a little bit of a better result if you had, 1,000 points instead of 100, for example, to choose from, and reserved, 200 instead of 20. So now I'm going to try to fit an 8th degree polynomial to this data, and I'm just going to pick the number 8 at random because I know it's a really high order, and it's probably overfitting. So let's go ahead and fit our 8th degree polynomial using np.poly1d, np-polyfit, using x, y, and 8, where x is an array of the training data only, and y is an array of the training data only. So we are fitting our model using only those 80 points that we reserved for training. And now we have this p4 function that results that we can use to predict new values. So let's go ahead and plot the polynomial this came up with against the training data. And we can scatter our original data here for the training data set. And then we can plot our predicted values against them. So you can see here, it looks like a pretty good fit, but clearly it's doing some overfitting here. What's this craziness out here? I mean, I'm pretty sure our real data, if we had it out here, wouldn't be crazy high, as this function would implicate. So this is a great example of overfitting your data. It fits the data you gave it very well, but it would do a terrible job of predicting new values beyond this point, right? So let's try to tease that out. Let's give it our test data set. And indeed, if we plot our test data against that same function, well, it doesn't actually look that bad. We got lucky and none of our test data is actually out here to begin with. But you can see that, it's a reasonable fit, but it's far from perfect. And in fact, if you actually measure the R-squared score, it's worse than you might think. So we can do that here using the R2 score function from scikit-learn metrics. And we just give it our original data and our predicted values, and it just goes through and measures all the variances from the predictions and squares them all up for you. And we end up with an R-squared score of just 0.3, so not that hot. And you can see that it fits the training data a lot better, which, with an R-squared value of 0.6, which isn't too surprising because we trained it on the training data. The test data is sort of its unknown, its test, and it failed the test, quite frankly. 30%, that's enough. So that's an example of using train test to evaluate a supervised learning algorithm. And like I said before, Pandas has some means of making this even easier. We'll look at that a little bit later, and we'll also look at more examples of train test, including k-fold cross-validation later in the course as well. And you can probably guess what your homework is. So we know that an 8th order polynomial isn't very useful. Can you do better? So I want you to go back, run this IPython notebook all the way through, but use different values for the degree polynomial that you're going to use to fit. So change that 8 to different values and see if you can figure out what degree polynomial actually scores best using trained test as a metric. So where do you get your best R-squared score for your test data? What degree fits here? So go play with that. If you have any problems, post in the discussions, but it should be a pretty easy exercise and a very enlightening one for you as well. So have some fun with it. So that's trained test in action. Very important technique to have, and you're going to use it over and over and over again to make sure that your results are a good fit for the model that you have and are a good predictor of unseen values. So great way to prevent overfitting when you're doing your modeling. Let's move on.